Hi everyone, welcome back to ChemHelp ASAP. Today we are going to be talking calorimetry and we're going to do lots of calculations. Let's get started. So calorimetry is measuring energy for either a physical or a chemical process. Now, before we can start actually measuring that energy, we need to define terms and also get a formula for how we're going to calculate this. So first, let's talk about specific heat. Specific heat is just the amount of energy needed to raise the temperature of 1 gram of any substance 1 degree Celsius. So the units of specific heat are going to be joules. This is the amount of energy needed per gram. Remember, we're raising the temperature of 1 gram, and per Celsius per 1 degree Celsius. Here is a table with specific heats of some various substances. The higher the specific heat of a substance, the more energy is required to raise the temperature. So you can see here for water, the specific heat is 4.184 as opposed to lead down here at 0.130. This means if you have 1 gram of water, you're going to need about 4 joules of energy to raise that 1 gram of water 1 degree Celsius. But if you have 1 gram of lead, you only need 0.1 joules of energy to take that up 1 degree Celsius. This is why, one, it takes so long to boil a pot of water. You have to transfer a lot of heat to get that temperature increase, and also why when you get that pot of water boiling, even if you turn the heat off, it stays hot for a long time. But your pot maybe is made of aluminum. This is going to heat up very quickly and cool very quickly, which makes it a great conductor for heat from your burner to your water. So now that we understand what specific heat is, how do we calculate the energy for a physical or a chemical process? Well, this is the equation we use right here. Q equals mcΔT. Q is the energy required for whatever you're doing, either again a physical or chemical process. M is your mass of your sample. C is your specific heat of your substance. Delta T is your temperature change, and specifically this is final temperature minus initial temperature. And it is really important that you always take the final temperature minus the initial temperature. This is going to give you the correct sign for your delta T and then often for your Q. Okay, let's see some numbers. Let's work some problems. Here's our first problem. How much heat is required to take 525 grams of water from 25 degrees Celsius to 100 degrees Celsius? And we're given the specific heat of water. So we're basically going to try and boil a pot of water here. Starting with our Q equals mcΔT, let's plug in what we know. We know our mass, that's 525 grams. We know our specific heat, that's 4.184 joules per gram times Celsius. And here is our temperature change. Remember, we always want to go final minus initial. So our final temperature is going to be 100 degrees C. Our initial temperature was 25 degrees C. This gives us a Q of 1.65 times 10 to the 5th joules. This is a positive value of Q, which means it is an endothermic process, which means we are going to have to add heat, which makes sense. Yes, you have to add heat to heat water from 25 to 100 degrees C. Okay, let's do another problem. If 525 grams of iron absorbs the same amount of energy, what will its final temperature be if it is originally at 25 degrees Celsius? And we're given the specific heat of iron. Okay, so it took us 1.65 times 10 to the 5th joules to heat up this 525 grams of water. And if we take that same energy and we plug it into iron, do we get to 100 degrees Celsius or do we get higher or lower? Let's find out. Again, we're still using Q equals mcΔT here, but this time we know our Q. So our Q is what we calculated in the above problem. We know our mass of our iron. We know our specific heat of our iron. But what we want to know is our final temperature. So our delta T looks like this, where our T final we don't know, but we're going to subtract it from our initial temperature, which is 25 degrees Celsius. Again, it's really important that you always go final temperature minus initial temperature. So, solving for our final temperature, we get a final temperature of 723 degrees Celsius. Wow, that is a lot hotter than 100 degrees C for our pot of water. Why? Why does our iron go up so much higher? Well, it's because the specific heat of iron is so much smaller than water. Remember, it takes a lot of energy to heat up water, but iron is about 1/10 of that. On to our next problem. Now we have an unknown metal with mass of 59.7. It's going to release 35.7 kilojoules of energy. And if the metal was originally at 900 degrees Celsius with a final temperature of 235 degrees Celsius, what is the specific heat of the unknown metal? And then we need to identify that unknown metal. Still using our good old Q equals MC delta T. Okay, so we know Q, we've got the energy that's released. We know our mass here. We do not know our specific heat. That's what the question asked us for. And we do know our initial and final temperatures right here. So let's plug all this in. First, I convert my kilojoules to joules. That's really easy. You're just moving the decimal 3 places to the right. Notice that this is a negative joules. That's because this is releasing energy. Our mass, of course, is 59.7. We don't know the specific heat. That's what we're solving for. Our final temperature is 235, and of course, our initial temperature was 900 degrees Celsius. Working through our algebra, we get a specific heat of 0.897 joules per gram times degrees Celsius. Well, let's see if we can identify this. So let's go back to our table from the previous slide, and we can see that this metal is going to be aluminum with, again, a specific heat of 0.897. Another type of calorimetry calculation is when you have two substances that are allowed to reach thermal equilibrium. Let me show you what those calculations look like. Okay, so let's read through this problem. 92.9 grams of an unknown metal is heated to 178 degrees Celsius and dropped into 75 milliliters of water at 24 degrees C. The two substances are allowed to reach thermal equilibrium. The final temperature of both is 29.7 degrees Celsius. Assume the density of water is 1 gram per milliliter. The specific heat of water is 4.184 joules per gram times degrees Celsius. What is the specific heat of the unknown metal? And again, what is the identity of the unknown metal? So we have two substances in this problem. We have a hunk of unknown metal and we have water. The key thing here is these two substances are put in contact with each other, i.e. the hunk of metal is dropped into like a pot of water, I guess, and they're allowed to reach thermal equilibrium. Remember, what is thermal equilibrium? Well, that is when the heat transfer is finished and the two substances are at the same final temperature. So that means in this case, the heat released by the metal, because the metal is hot, is fully absorbed by the water. We do assume that we don't lose any heat to the surroundings. So what this means mathematically is our Q of our metal is equal to the Q of our water, with one important exception. The metal releases that heat, so it has a negative Q value. The water is absorbing that heat, so it has a positive Q value. So this equation is the same as this equation. So you can see I've just taken my Q and turned it into MC delta T for each substance. The important thing in this step is to make sure you keep all the information with the metal, and the water with the water. So what I see often is like a specific heat might get flip-flopped and you accidentally put the specific heat of metal over here and the water over here. So you just want to make sure you keep track of what numbers belong to the metal and what numbers belong to the water. Okay, let's plug in the numbers from our problem. So we know the mass of our metal is 92.9. We do not know the specific heat of the metal. Again, that's what we're trying to calculate. We know our final temperature is 29.7, and we know the metal started out at 178 degrees Celsius. Okay, so that's the metal taken care of. Now for the water, we have 75 grams of water. Again, we know that because while we were given the volume of water, we were also told that we can assume that this density is 1-to-1. So 75 milliliters of water gives you 75 grams of water. The specific heat of water, of course, is 4.184. Our final temperature of our water is the same final temperature as our metal. Remember, they have reached thermal equilibrium. They have the same final temperature, and that's 29.7, but the water started out at 24 degrees Celsius. Just like before, it's always really important that these delta T's are final minus initial. Otherwise, your signs are going to get messed up and you're going to get really weird answers. But keeping our signs straight, being careful with our algebra, we get a specific heat of metal of 0.130. And the only thing left is to identify this unknown metal. So let's go back to our table from our previous slide. So specific heat of 0.130 means that this unknown metal is lead. Let's do another of these type of calorimetry problems, but this time let's find our final temperature. A copper ball with mass of 248 grams at 314 degrees Celsius is dropped into 390 milliliters of water at 22.6 degrees Celsius. The two substances are allowed to reach thermal equilibrium. That's very important. What is the final temperature of both? Again, we can assume the density of water is 1 gram per milliliter, and the specific heat of water is again 4.184 joules per grams times degrees Celsius. And they give us a specific heat of copper is 0.385 joules per gram times degrees Celsius. Okay, so again, these two substances are allowed to reach thermal equilibrium. That means our final temperature is the same for both of them. The heat released by the copper is going to be perfectly absorbed by the water. So our Q of our copper equals our Q of our water with the important addition of our negative over here. So we can take these two Q's, turn them into mcΔT, and here is our equation. Again, these final temperatures here are the same variable, but our initial temperatures do need to be specific to that specific substance. Sometimes the challenge of these problems is keeping everything organized and straight so that all of the numbers go in the right place with the right sign. So let's do that for this problem. Let's put our numbers in the right place with the right signs. We've got our mass of our copper, our specific heat of our copper, again, our final temperature, which we're trying to solve for, and this is the initial temperature of our copper. Now for the water, here is our mass of water. Remember, we're assuming the density is 1 gram per milliliter, so these 390 milliliters become 390 grams. Specific heat of water, again, final temperature minus the initial temperature of the water. And at this point, we've got one equation, one unknown. We can solve for this TF. So keeping all of our signs straight, being careful with our algebra, we get a final temperature of 38.7 degrees Celsius, which makes sense. Our final temperature should be higher than what our water started at, but should be much lower than where our copper started. When working these problems, if you get a final temperature that doesn't make sense, like if you get a final temperature that is below 22.6, usually what that means is you have a sign error somewhere. So just be really careful with that algebra. Our final type of calorimetry calculation involves a chemical reaction. Here is our question. When 0.75 liters of 0.12 molar barium nitrate is mixed with 1.25 liters of 0.95 molar sodium sulfate, barium sulfate precipitates. Okay, so we've got a precipitation reaction here. Initially, both solutions are at 24.3 degrees Celsius. When they are mixed, the temperature increases to 28.1 degrees Celsius. So we have an exothermic reaction going on here. Assuming the specific heat of both solutions are the same as water and the density of the solutions are 1 gram per milliliter, how much heat is evolved? And then what is the enthalpy of reaction per mole? So we've got two questions to answer here. Let's first figure out how much heat was evolved from this reaction. Whenever we have a chemical reaction, the first thing we want is a balanced chemical equation. So we have barium nitrate reacting with sodium sulfate. This is a double replacement reaction. We form barium sulfate as a precipitate and sodium nitrate. The other way you can think about this reaction is with a net ionic equation. And that would be your barium cation plus your sulfate anion going to form barium sulfate. Either reaction you want to use is totally fine. Just make sure they're balanced. This is a calorimetry calculation. We're going to use our Q equals mcΔT. This, of course, is for our solution. Before we can plug numbers in, we need to do a little bit of what I call a side calculation. We need to figure out the mass of this solution. How do we do that? We first figure out our volume. So our mass of our solution, we're going to take our two volumes that we added. So we added 0.75 liters of our barium nitrate and 1.25 liters of our sodium sulfate. That gives us a total volume of 2 liters. Well, what is the mass of that 2 liters? Remember, the density of the solution is 1 gram per milliliter. So first taking these liters, converting to milliliters, and then using the density, we get a mass of 2 times 10 to the third grams. Okay, now that we have the mass of our solution, we can plug into our Q equals mc delta T. So here is our mass. Again, we assumed that the solution has a specific heat of water, so we're going to use our 4.184. And what is our change in temperature of the solution? Well, our final temperature was 28.1, and our initial temperature was 24.3. That gives us a Q of 3.18 times 10 to the 4th joules, or 31.8 kilojoules. Okay, so that tells us how much heat was evolved, but now we need the enthalpy of reaction per mole. Well, to calculate our enthalpy of reaction, what we want to do is we want to take our Q of our solution divided by our number of moles. Well, what number of moles do we use here? We need to figure out which of our reactants is the limiting reactant. So let's figure out how many moles of each of our reactant we have. So to figure out our moles of barium, again, I'm going by my net ionic equation here, but if you wanted to, you could go by your molecular equation. My concentration of barium is the 1.2 molar, so that's 1.2 moles of barium over 1 liter of solution. I used 0.75 liters, so I have 0.9 moles of barium. I do the same thing for my moles of sulfate. My concentration was 0.95, so again, that's 0.95 moles of sulfate over 1 liter of solution. I used 1.25 liters of that solution, so I have 1.19 moles of sulfate. The great thing about this reaction is this is a 1-to-1 stoichiometric ratio, which means my limiting reactant is just my smaller number of moles. So that is the moles I'm going to use in my equation. So now to calculate delta H of solution, I just take my 31.8 kilojoules divided by 0.9 moles, and I get a delta H of 35.3 kilojoules per mole. That was a lot of work to find an enthalpy. I hope you found this video helpful, and thanks so much for watching.